Today, we're going to talk about regression analysis and highlight some common regression misconceptions, especially for multiple regression. Regression is extremely simple. It's just y equals mx plus b. But because it's so basic, it's easy to accidentally misunderstand what exactly the numbers really represent. After watching this video, you'll have a better understanding of the numeric implications of the simplified y equals mx plus b interpretation, and ways you can fine-tune your analysis and interpretation to make sure you get results that are really consistent with what's actually happening in the data. It's gonna take some time to cover everything, but we'll try to make it intuitive, no arithmetic, no computer coding, lots of visuals. So settle in, get comfortable, and we'll get started. Hi, Ray Tanzer here with the Brown Pediatrics Department. Let's get into regression. Regression means y equals mx plus b. And the more you can think in terms of this basic equation, the better, because it's underappreciating this logical simplicity where misinterpretations often come from. To start, let's draw a chart we could analyze using regression for something that's really obvious. What if we looked at heights across kids of different ages? And everybody knows that kids get taller as they get older. I'm going to draw a picture to make it really easy to understand. So we've got an x-axis representing age, and on the left side is 0 years old, and on the far right is 18 years old. Then we'll have a y-axis for height, so we'll have 0 feet at the bottom and go all the way up to 6 feet at the top. And it's just making these data points up here, but we can draw on a bunch of hypothetical data, and we'll make it really obvious that as you get older, you tend to get a little bit taller. Done. So if we have a regression analysis, we're going to want to summarize this relationship, characterize how much taller kids get on average with every year. We want to do this because it gives us some sense of how quickly kids tend to grow, and we might like to test whether or not the association we see in the data is statistically meaningful. So how does that happen? Well, we'll figure out what line best characterizes the association we see. More specifically, this is using calculus to draw a line that gets as close to the data points as possible. It's not going to get any specific data point perfectly accurately, but it'll get as close as it can to as many data points as it can. So when we say regression is y equals mx plus b, that's what we mean in a very literal sense. We can interpret the average of the outcome y as a function of an x variable with a slope coefficient m, plus b, the intercept, the point at which the regression line crosses the x-axis. And really, it's this regression misconception has largely to do with how we focus on the association but tend to neglect the intercept. So the regression association represents rise over run. How much change in y is associated with a 1-point increase in x? Great, no problem there. But if we don't think about what the intercept represents, we might not draw the right conclusion. Some say that it's not really meaningful, it's just an artifact of math. And that could be true in some settings, but it also may not, and it all depends on how you set up the analysis. The intercept, it represents the point where the regression line intersects with the y-axis. And when would the regression line intersect with the y-axis? Well, when the x value is equal to 0. So that's what the intercept represents. It represents the average of y at the point where x is numerically equal to 0. And that's why it may or may not be useful. Really, it all depends on whether or not there's a meaningful interpretation of what a value of 0 would mean for the x variable. An example of when the y-intercept would be meaningful. Let's say you're doing a longitudinal study. On the x-axis, you would have time be the x variable, so you'd code baseline at 0, and then you would extend out to the right for, say, 3 follow-up occasions. And then you would want to look at, on the y-axis, some outcome is decreasing over time, showing how patients get healthier over the follow-up occasions. If you did that, then the intercept would be very relevant. It would represent the average of the outcome at baseline. And in this case, this would provide important context on where people started. The intercept could also be truly irrelevant, just an extrapolation of the data. Say instead you looked at blood pressure of people getting older, but you only had data on people ages 50 to 80. So we'll have an x-axis which starts at 0, but goes all the way up to 80, and all the data are on the right half of the graph, because that's all the ages that you collected data on. And yes, we can see that blood pressure increases as people get older. The points get higher as we go further to the right. But the intercept all the way on the left side where the y-axis intercepts with this regression line, well, that's got a value of 0. So what would the y-intercept represent in this case? It would represent the average for newborns, people who are 0 years old. And you definitely aren't interested in that average. See what I mean by y equals mx plus b is really basic? But that's the challenge here, interpreting it properly. Importantly, we can change the analysis to obtain more meaningful results. In a process called centering, we can move the y-intercept. So let's go ahead and cut off the y-axis in this last graph and pick it up and move it to a better place. That's what centering is. Mathematically, it's subtraction. If we wanted the intercept to represent the average at 50 years old, for example, we could subtract 50 from each of the ages in the data set, so that a value of 0 on x corresponds to 50 years old. You could also do the average for age across everybody in the data set, so that the average blood pressure corresponds to average age. It's up to you, but understanding the simplicity that y equals mx plus b plays out here, you can set it up to get a meaningful result for whatever you need. That's the basic formulation for regression analysis, which has really obvious parallels to y equals mx plus b. But we need to talk about categorical x variables before we get into multiple regression analysis. As before, the interpretation of the intercept is often misunderstood, but that has important implications for everything else. Let's say we're talking about height again, but this time you compared boys and girls, or really more specifically, people with an XY chromosomal makeup and people with 2 X's. So for now, we'll draw an x-axis with no numbers marking out yet. We'll get to that in a moment. But the y-axis will have height again, going from 0 feet at the bottom to 6 feet at the top. And we'll just draw some points vertically in 2 columns for girls and boys. So the points on the left will represent boys, and the points go a little bit higher. And then the points on the right will be the points for girls. And then we can say that boys tend to be a little bit taller than girls, which is why the points on the left are a little bit higher than the points on the right. But this can help us compare the 2 groups using regression analysis. We can still fit this right into a y equals mx plus b framework, but we have to set it up a little bit differently. Because the results represent the averages at a cross-section of X data rather than individual data points, we could draw a line from the average for boys to the average for girls. The slope of this would then represent the difference in averages between girls and boys. In this case, it would be a negative value, sloping down and to the right, since girls tend to be a little bit shorter than boys on average. We can also add on some labels to the x-axis now. If the slope represents rise over run, and we want the coefficient to represent the absolute difference in average heights for girls and boys, we'll make that x-axis input be 1 point apart. So we'll use dummy codes. An x value of 0 for the column on the left representing data for boys, and an x-axis value of 1 for the column on the right representing data for girls. And at this point, many will focus on that slope coefficient representing the difference in averages between girls and boys. And that's great, no problem there. But as before, I want to make sure we really understand what that intercept represents. That's our next regression misconception. So if we want to interpret that intercept, that really, it doesn't represent the overall average or something like that, but it represents the average at whatever value of x is equal to 0, because this all goes back to y equals mx plus b. So in this case, it's pretty explicit. If we coded the column on the left for boys with a dummy code of 0, that means that the intercept represents the average for boys. And that's why it matters, because you can choose what group you code with a value of 0 as the reference group. It doesn't make a huge difference if you only have 2 groups, because there's only one difference to calculate between the 2 groups. But what if you had 3? In this case, for 3 or more groups, you would have to choose one common reference group against which each dummy code is compared. In other words, each coefficient in the analysis would be in reference to the same common group. Additionally, because of this, the raw regression model itself may not provide the information that you're looking for, not if you just looked at the individual itemized regression coefficients. Let's go to an example. Let's say you've got an experiment and participants are randomized to either a placebo condition or a current of standard treatment condition, or maybe some new experimental treatment condition. To analyze this with regression, you need to pick a reference group for dummy codes, which each of the other groups would be compared in reference to. So let's say you pick the placebo condition. If you did this, you'd wind up with 2 dummy codes, a dummy code identifying participants in the current standard of treatment group with a value of 1, and then you'd have a dummy code for identifying participants in the new experimental treatment group with a value of 1. The regression coefficients would then represent the difference in averages between the placebo group and each of the current standard of treatment group and the new experimental treatment group. But what if you wanted to look at the difference between the current standard of treatment and the new experimental treatment? Importantly, this could provide a unique insight to the research question, because what if you wanted to tell if the new experimental treatment is really that much better than what's currently on the market, or if it's more or less same thing as we have already? Unfortunately, there isn't one coefficient that represents that information the way this model is set up. You need to subtract the 2 difference coefficients to tell. That's why regression analysis is logically efficient, but can be very misleading. To interpret regression correctly, you cannot separate the coefficients from the y equals mx plus b formulation. Even if the intercept isn't the primary focus of interpretation, understanding what the intercept represents can help contextualize what everything else means. This covers the basic implications of how regression analysis relates to y equals mx plus b. Really though, this is much more important when we scale things up to multiple regression. But I know this is a lot of information all at once, so if you need a minute to get another cup of coffee or scroll through your phone, or whatever it is you do, now would be a good time to pause the video and take a break. Let's talk about multiple regression. So before we were looking at height based on age and chromosomal makeup, but really you want to understand child development, you need both. Boys tend to be taller, but girls also tend to get a growth spurt a bit earlier. Which group is taller really depends on how old the kids are when you compare them. Younger girls being taller than younger boys, but older boys being taller than older girls. That's a lot of words. Let's draw it out to make sure we really understand what's going on here. So we'll draw on the x-axis, it'll be age again, so 0 on the far left and 18 on the far right. The y-axis will be height, so 0 feet on the bottom and then 6 feet at the top. Now let's just draw some data points for boys with purple dots. So as you get older, you tend to be taller. And just like before, great. And we can do a purple line through the middle. So the regression analysis going from bottom left towards top right. And we can summarize that with our favorite y equals mx plus b. So we'll get a slope representing the association between age and height for boys. And we'll have an intercept representing average height at age 0 for boys. And now let's add some data on for girls. This time we'll use some red plus signs to make sure it's clear. We'll still have the positive association, just like before, showing that when you get older, you tend to be a bit taller. But this time we'll show that younger girls tend to be a little bit taller than younger boys, and older girls tend to be a little bit shorter than older boys. And we'll still have that positive association in there. We'll have a red regression line for girls going from the bottom left to top right, but the slope for girls in this red line isn't going to be as steep as the purple line for boys. Additionally, it's not going to get as high at the top right. And if we go look at the left, where the line intersects with the y-axis, the intercept is going to be a little bit lower for boys than it is for girls. So how can we analyze this in y equals mx plus b format? Really, it's not too bad. It just means that we're going to need some more coefficients. And in fact, we have two sets of y equals mx plus b equations here, one for girls and one for boys. Fortunately, we have a set of dummy codes that can help us distinguish the data from boys from the data from girls. So we have all the information we need, we just got to set it up. We'll estimate a standard y equals mx plus b equation for the purple line representing data for boys, just like before, where we've got an intercept that represents the average at whatever value of x is equal to 0. And then we'll have a slope coefficient for age, and this represents the rise over run, and we're going to call that the main effect of age. Next, we'll need a new intercept and slope for the red line, representing data for girls. But we already have an intercept and slope in this regression model based on the data for boys. So the coefficients we generate will have to mean something slightly different. Specifically, they will represent the differences in intercept and slope between girls and boys. So there will be a main effect of sex, which is like the categorical dummy code we had before, literally representing the difference in averages at age 0 for boys and girls. And then we'll also have an interaction term between sex and age, which represents the difference in slopes for the association between height and age between girls and boys. That's why regression analysis is so logically efficient, but unintuitive. The whole analysis boils down to two sets of y equals mx plus b equations, but only one of the equations is directly provided by the regression model itself. To get the y equals mx plus b intercept for girls, you need to add the intercept, representing the average at age 0 for boys, to the main effect of sex. And to get the slope for age for girls, you need to add the main effect of age to the interaction between age and gender. Regression analysis can answer most questions comparing group means and estimating associations, but the model itself is a bit confusing unless you think about it in this very basic, simplified y equals mx plus b format. I almost never report the raw regression model itself. My attitude is the regression model is better understood as a pantry of ingredients. You don't eat the raw ingredients right out of the pantry. You usually cook them together, combine them based on a recipe. With a regression equation, you can estimate any average, any difference in averages, any slope, any difference in slopes, any piece of information you need about the data you have. But importantly, the specifics might not be represented by the raw coefficients themselves, and you might need to make sure that they line up with the regression equation you're trying to interpret. This has direct implications for the conclusions you would draw. And as before, the regression misconception goes back to the intercept and what a value of 0 represents for the x variables. If we look at the main effect of gender, that literally represents the difference in intercepts for the two y equals mx plus b equations. And because of that, the interpretation depends on what value of 0 represents for age. Let's cut out that y-axis, just like we did before, to visualize the impact of centering. And so if this intercept is off to the far left side over here, the main effect of gender would imply girls are taller than boys because the red line for girls is currently above the purple line for boys. If we move the intercept to the far right, now the purple line for boys is higher than the red line for girls. So the main effect of gender would imply that boys are taller than girls. And if we go to the intercept where the lines intersect, the main effect of gender would be a value of 0, implying no difference between the two groups. The same issue shows up for the main effect of age. Since there's only one y equals mx plus b equation that can be directly interpreted as representing the association between age and height without adding any coefficients together. The main effect of age would represent the association between age and height for whichever group is dummy coded as a value of 0, in this case boys. This is what I mean when I say regression is very simple and logically efficient, but can be unintuitive. You're probably looking for some practical implications. If you want to interpret regression accurately, just keep in mind that this isn't mathemagic and that association is really a concept, not an equation. Regression means we drew a line through the data points, and this is the y equals mx plus b equation that summarizes the line we drew. If you're reading an article, keep in mind what a value of 0 for the x variables would represent, because that will be relevant to what the coefficients represent. If you're doing your own analysis, consider what information you want the regression model to represent and how the choice of what a value of 0 is coded as might change the conclusions that you draw. This is important because it will impact the direction of differences, the direction of associations, and even the p-values you get. Last note. In this discussion of multiple regression, we assumed there was an interaction between the x variables included. But honestly, not everybody includes those interactions in there, not for every analysis. I would generally recommend including the interaction effects for all variables included in the analysis because you could get very different results depending on whether or not you include it. If you do not include the interaction effect, you have assumed that the y equals mx plus b equations have parallel slopes and equal intercepts for all the different subgroups in the data. Is that plausible? Even if the interaction effect isn't significant, it may be relevant to obtaining meaningful results for all of the main effects included in the analysis. Because it's possible that by excluding the interaction effect, it will drag the line up or drag the line down to meet the constraints of assuming parallel slope coefficients. That's just a very long way to say it's another situation where you get different associations, different group differences, and different p-values based on whether or not you include the interaction effect within the analysis. I generally recommend selecting only a few carefully chosen x variables, 2 or 3 tops, making sure that you collect data on all possible combinations of those x variables using stratification and blocking. If you represent all of the possible combinations of these variables, you can confidently include all interactions in the analysis. Otherwise, you would presume parallel slopes, which to me seems like a big presumption. If the slopes are truly parallel, let the data decide. I'd also recommend thinking about which y equals mx plus b equations you need to test your hypothesis, and using the regression model solution to recreate these y equals mx plus b equations for any subgroups you're comparing. This isn't mathemagic, and association is just a concept. At the end of the day, all we're doing with this is drawing lines through the data points. If you interpret the model with the simplicity that reflects the math actually being performed, it reduces the risk of accidental and unnoticed misinterpretation.